Okay, good morning, everyone. So today we are back to actually review the Term 1 database questions, the remaining questions from week 6 till week 10. So there are 4 questions in total. So we'll start from Term 1, week 6 database question, which is from St. Patrick's School 2021 prelims. All right. Now, in any database question, you must have the key skill of annotating the information. That's number 1. By annotating, you are making sense of the information so that later on you can locate whatever info you need more easily. The second important skill is after you annotate, you must try to paraphrase, try to understand, try to highlight the main trends that are told to you in the question. So we are going to do that very effectively for this particular database question from St. Patrick's School. So let's start. Now, the first thing we have to take note of when annotating is always the header, or what you might call title. All right. Now, for pure chemistry, your database question in the O-levels will always have a header. Sometimes there can be even subheaders. Subheaders means for every section, there's a different header, right? So the header obviously is this: ionization energy of group 2 metals. That's the first header that you see. It's in bold. All right. So immediately you realize it's about group 2. It's about this concept of ionization energy. So now you have to think, after reading this header, have you learned this before? Well, you know what is group 2. Group 2 is basically magnesium, calcium, barium. These are elements found in group 2 and they are all metals. So group 2 you know, but you may not know what is ionization energy. And indeed, ionization energy is not a concept taught to you in the O-levels. Right? You may have learned it if you came for Chemistry Olympiad, but if you have not come for Chemistry Olympiad, you wouldn't know this. So it's clearly, this part is new to you. If it's new to you, do you panic? The answer is no, please don't. All right? You know already that the database will present a new context to you. But whenever we give you a new context, the info is always given in the question itself. So you have to now look out for the second thing, which is, what are the definitions given to you? Clearly, you need a definition of ionization energy, or else you can't start. Okay? Besides definitions, they will also give you trends. All right? So now let's use a different highlighter ink to highlight some of these definitions and trends. So the first trend that you can read is really what I've highlighted in blue. Electron is more strongly held by the nucleus. A higher ionization energy is needed. All right, so this is clearly a trend. How do you recognize trends? You look for words like more, higher, lower, less. So these are words that are comparative. You are comparing things. More strongly held electron, higher IE. All right, so this is a skill. Okay. Now, besides that, you will also want the definitions. So this is the definition of first ionization energy, which is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to produce 1 mole of gaseous ions with a charge of 1+. Right? So this is crucial. You are removing 1 mole of electrons from 1 mole of atoms in the gaseous state. All right, and what this forms is an ion with a 1+ charge. Okay, it is not 2+, it's just 1+. So this might look a bit strange to you because it's about group 2, right? So why is it that we talk about 1+? This is because for group 2, they need to lose 2 electrons. So first IE is not losing 2 electrons yet. First IE is just losing the first electron, right? So in a layman term, okay, so you can see I'm trying to reword so that you can understand better. You are losing the first electron to form the 1+ ion, 1+. So what is the 2+? The 2+ obviously requires the second IE as well, which the definition is shown below. So the second IE is losing the second electron to form 2+ ion from 1+. Okay, so you can see Mr. So doesn't just highlight. Mr. So will annotate with words. And that's what you need to do, because that's how you make sense of something. Okay? Then you know this is about group 2, right? The header says it's about group 2 metals. So if you have highlighted the header, you keep in mind, okay, this is about group 2. Group 2 is like magnesium. Magnesium, does it form Mg plus or does it form Mg2 plus? So if you think back, okay, Mr. So has taught you all before, under atomic structure, group 2 has 2 valence electrons. So it will lose 2 valence electrons to form the ion with a 2 plus charge, right? So you know by now, group 2 will form 2 plus. So definitely the question later on will ask you, how much energy is required to form the 2 plus charged ion? So for example, if you start off as X in the gaseous state, you are going to form X2 plus. It's a group 2 metal, right? Is this going to be a one-step process? Based on what you have been told thus far, looking at the equations, can it go from X, no charge, to 2 plus immediately? Well, the answer obviously is unlikely, right? It's quite obvious the way the question information is phrased, you have to go first IE first. First IE allows you to form the plus. Right? Then from the plus, you go to 2 plus. Meaning, to form the doubly charged ion, you need to add the first and the second. So the total energy change is the first IE plus the second IE. This is what the information tells you, all right? Now, you might think this is obvious to you, but actually let me say that this is quite a common mistake that many students, even at A-level, will make. They think that to get the 2 plus is just the second IE. It's not. Remember, it's a 2-step process. You need to form the 1 plus first, then the 2 plus, which means you need to have the first IE, then the second IE. So the total enthalpy change is the sum of the first and the second, all right? So with this, we have basically paid attention to the definitions and the trends. Definition of first and second IE, as well as the trend, right? If the electron is more strongly held, a higher ionization energy is needed. So all these have been highlighted in blue. You should have highlighted these in blue and also tried to make sense of it, all right? So with that, we can move on to the table. Now, you are very often given information in a table or information in a graph. Whenever we are given numbers in a table or graph, it is good to write out the trend. So what is the trend here? The trend is in terms of reactivity versus ionization energy. I think this is quite clear, right? You are given reactivities, you are given IE. So it's quite obvious. The more reactive the metal, the lower the IE. Both for first and the second IE, you can see that this is the trend, the relationship. All right. Whenever you are given numbers, please write the trend out. Even if the question doesn't require it, you should do it. All right. Ken? Okay, so at this juncture, can I just check everyone in the Zoom meeting is okay with this and you have annotated accordingly? If you have, can you please give me a thumbs up? Okay, so you can see just based on page 1 alone, you have already highlighted many pieces of useful information. And with this, honestly, you can solve most of the questions, I believe. Okay? Now, I haven't even seen the questions, but I can tell you that this will be what is tested, just based on the reading of the text. Now, before we move on, so you will have to highlight and pay attention to the header or title, the definitions, and the trends. The third thing you should definitely pay attention to is chemical names and numbers. So this is what I've been highlighting to you every single time we go through a question. You need to make sense of the question by paying attention to what is the chemical name and what are the numbers given to you. Because usually when we give you numbers, you may have to do some calculations like mole concept. Okay? Now, the final thing that you should pay attention to, in chemistry, you can't run away from equations. So if the question information includes equations, please pay attention to them. Over here, you can see you have two equations already. X becomes x plus becomes x2 plus. That's an equation, right? A half equation. Now, importantly, it's all in the gaseous state. Why is it in the gaseous state? This is because the ionization energy is defined for the gaseous state. All right. So clearly, you can't do the calculation if it's not in the gaseous state. Okay, so these are the four main things to take note of in every single database question. The header, the definitions and trends, chemical names and numbers, finally, equations that are given to you. Okay, and with that, let's go to page 2 quickly. The second page, again, is quite similar, right? You are given another header. This is important. You recognize it's another header because it's a bolded statement, all right? Now, this obviously is a different concept. Now they're talking about thermal stability of carbonates of group 2 metals. Oh, you should have learned this before. The moment you read thermal stability of carbonates, you must think, which chapter have you learned this? You have learned this under metals. Chapter 14, metals. You have learned the pattern and trend. The pattern and trend is this. The more reactive a metal is, the more thermally stable the carbonate. Therefore, the higher the temperature needed. Right? This is what you have learned under metals. More stable carbonates need a higher temperature to decompose. And if the metal is very reactive, such as potassium, sodium, they form very stable compounds that don't decompose. So potassium carbonate, sodium carbonate don't decompose at all. Okay? So this is under metals, what you memorized, right? But now let's look at the graph. Beyond just highlighting the trend that you have memorized, if you look at the graph, does the graph support this trend that you have memorized? Is it true that the more reactive the metal is, the higher the temperature needed? If you just look at a graph, as it becomes more reactive means from beryllium to barium, right? More reactive. Least reactive, most reactive metal. So from beryllium to barium, the reactivity increases. However, does the carbonate seem to become more stable for every single one of them? And the answer is, of course, no, right? Quite clearly, the temperature goes up, goes up, goes up. That means it's more stable, more stable, more stable. You need a higher temperature to decompose it. But it's not true for barium. Suddenly you see, oh, there's an exception. Whenever you do trends, you need to differentiate between the general trend and highlight any exceptions. And that's why it's important to write down the trend and highlight the exceptions, because I can guarantee you they will ask you about the exception somehow later on in the question. So even without looking at the questions, I know this will be asked. So quite clearly, there's an exception here, which is of course barium carbonate. So let's keep that in mind as we go on to do the questions. Okay? Now, so they did some experiments. They actually decomposed and heated 1 gram of the metal carbonate and the volume of CO2 measured. Okay, so what is this reaction? Basically, the carbonate of metal M decomposes to form the oxide and CO2 gas. All right. So if you were to look, the volume of CO2 tells you something. In particular, there is no CO2 produced for the final two carbonates, strontium carbonate, barium carbonate. No CO2. Why? Why will there be CO2 produced? The CO2 is produced from the decomposition. So the carbonate needs to decompose to get CO2. However, there is no CO2 at all for strontium and barium carbonates. This means there is no decomposition. Why will there be no decomposition of the carbonate? So now you think back. Which carbonates don't decompose? The most thermally stable carbonates. And why do you think strontium and barium carbonate are the most thermally stable? Because strontium and barium are the most reactive in group 2. So can you see, by writing this out, by highlighting the exceptions, zero CO2, that's an exception. Now you can start to reason out the answer to whatever question you need to do. Now, it may look like a very tedious process, like 10 to 15 minutes just doing something like this. 10 minutes is your rough benchmark. You should spend 10 minutes doing whatever you just did, the annotations. Because by spending this 10 minutes, I can guarantee the 12 marks later on, you will probably get about 9 or 10 out of 12. If I'm not wrong, they did ask, right? Why does strontium and barium carbonate produce no CO2? And that's the answer. All right. And so with that, I'm sure you can answer the questions very, very easily. Okay, so I shall not go through all the questions. Part A in particular is just reading the table of information involving the ionization energy and reactivity. So the second IE decreases down group 2. All right, simple. All right. Okay, moving on. Okay, can I just check everyone in the Zoom room? Can I move on? Have you finished copying the annotations on page 20? If you have, please give me a thumbs up so that I know that you're done as well. Thank you. Okay, now if you go to part B, I'm sure you can tell by now, this is exactly what I was referring to, right? To form Ca2+, you need both the first and the second, all right? Now, so the energy required to form 1 mole of the ions is first IE plus second IE. However, 1 gram is not 1 mole. 1 gram of calcium is just 0.025 moles of calcium. Okay, so once you know that, I think doing the question is really easy. 0.025 times the energy that you have just calculated. Okay, so you can see by really understanding the question, this question 3 marks easily gotten, easily obtained. On the other hand, if you had not annotated as thoroughly as I have, you would make a careless mistake, and hence you wouldn't get the 3 marks. All right. Now moving on. Now part C is what I want to focus on. A student proposes that the temperature at which group 2 metal carbonates decompose depends on the second IE. Is he correct? Give an explanation. Now, this is a very common kind of question. They will give you a claim, a student claim that a student commented that something, and then you will need to use the information as evidence to either support his comment or disprove his comment. So firstly, you got to determine, is it true that temperature at which the carbonates decompose depends on second IE? If it's true, there should be no exceptions, right? We already know by now, as you go down group 2, the second IE decreases. That means from beryllium all the way to barium, the second IE decreases. But does the temperature at which the carbonate decompose follow this same smooth, consistent trend? I think the answer is, of course, no, right? There is an exception, which is barium carbonate. Barium carbonate doesn't follow this trend, clearly. the temperature at which barium carbonate decomposes is lower than strontium carbonate. This is in spite of the fact that barium has a lower second IE. So barium doesn't seem to follow this trend. Therefore, we cannot say the student is correct. The student's claim is, he claims that it's true for all the carbonates, but it's not. When the question is phrased like that, you got to think, is there any exception? If there is an exception to this trend, then the student's claim is incorrect. Therefore, the student is not correct because of the exception of barium. So you can see the second IE decreases from beryllium to barium, but the temperature at which the carbonate decomposes, I left out one word, increases only from beryllium carbonate to strontium carbonate, then it decreases for barium carbonate. So if there's an exception, you cannot claim that this statement is true. Okay, so you must differentiate general trend from a trend that's always correct. In this case, the student wants to say that this trend is always correct. All right. Now, this student's claim is not correct because it sounds like it's true for all the group 2 metals. However, how can I make his statement correct? I can make his statement correct by adding just one word. And the one word that I add is basically, to make his statement correct, I must say that the temperature at which group 2 metal carbonates decompose generally. So you need to add a word generally. If I add this word generally, then the statement is correct. If no such word, then the statement is wrong. So there's a difference. Generally depends means if there's one exception, two exceptions, okay. The majority still follows this trend. Generally, they follow this trend. However, because there's no such word in the question, generally, this means that the statement is wrong. Okay, so we need to differentiate these two. All right. Now, and with that, I think part D is not difficult. We just went through that. Why no carbon dioxide is obtained from heating strontium and barium carbonate. We went through that already. All right. Now, moving on to part E. Part E is a calculations question. So again, right, as you can see, for any calculation, please highlight chemical names and numbers. Need this. All right. So the first thing you need to do is obviously you need to convert 122 cm cube of CO2 to moles. It's a mole concept question. The first step is always convert to moles. 122 cm cube must be converted to dm cube. All right, so you divide by 1000, then you divide by 24 to find number of moles. Once you have number of moles, it's not difficult, I think, because all you need to do is just use mole ratio to solve for the number of moles of the carbonate. Okay, so you can see it's a 1:1 ratio, 1 mole of carbonate to 1 mole of CO2. So if you have 0.0050833 moles of CO2, then you have the same number of carbonate. So once you have number of moles of carbonate, what do? You do not know what the group 2 metal is. So the only way to find out is to find its ARMR. So find the MR of the carbonate. How do you do that? Okay, it's MNMR. So MR is M over N, 1 grams over the number of moles. And once you have that, the MR, you just need to minus away the AR of carbon and the AR of the 3 oxygens. And that gives you about 137, which corresponds to barium. Okay, now I'm just going to zoom out a little bit. Okay, and please copy down the annotations first. Okay, then we're going to talk about something extra later on. But just copy down the annotations first and check that your answers are correct. All right. Once you're done, please give me a thumbs up as well so that I know that I can move on. Okay, good. Some of you say you have other solutions for part E. Basically, let the MR of the carbonate XCO3 be equals to like Y or be equals to X, and you solve algebraically. That's also fine. All right, Ken? All right, so I guess I may move on from here. Okay. Now, I hope you realize that we spent quite long trying to annotate something, and that's worth the time. Because once you annotate something, actually, the most of the marks, you would have gotten it. Now, you might be wondering, how does decomposition work? Now, this one don't need to copy. You can just refer later on to the OneNote content library. Now, let's take beryllium carbonate, for example. Now, beryllium carbonate decomposes. Beryllium carbonate is an ionic compound, right? Be2 plus, CO3 2 minus, ionic. But there's ionic bonding between the Be2 plus and the CO3 2 minus because they are oppositely charged ions, 2 plus, 2 minus. However, there is covalent bonding between the carbon and oxygen atoms in the carbonate ion. So between the C and the O inside the carbonate is covalent. That's why we say beryllium carbonate has both ionic and covalent bonding. Ionic between the ions, covalent between the carbon and oxygen atoms, all right, in the carbonate ion. Now, so because there's covalent bonding between the C and the O, they are shared electrons, right? So what happens is the electrons that are shared in the bonds, the covalent bonds, can be attracted to Be2 plus, and that's logical because electrons are negatively charged. Even though they are being shared between the carbon and oxygen, if you put them close enough to the Be2 plus, the Be2 plus ion can attract the shared electrons towards itself. This is called polarization. We say Be2 plus polarizes the shared electrons in the carbonate ion towards itself. So what happens is that the electrons start being drawn towards Be2 plus. It doesn't leave the covalent bond, but it's slowly being attracted there. As a result, there is lower electron density inside the CO covalent bonds, right? And covalent bonding requires electrons to be shared. If the electron density that is shared is lower, then the CO covalent bonds become weaker. So they need less energy to break. And that's why the decomposition happens. Decomposition is when the CO covalent bond inside the carbonate ion breaks. And that happens because the electrons that are being shared are polarized by the metal ion. Now, Be2 plus is a very small metal ion, all right? It's highly charged, all right? And that's why it's very effective at polarizing the shared electrons. Okay? Now, in contrast, if I change Be to calcium, bigger, Ca2 plus is a larger ion. As a result of that, it polarizes less. It has a lower polarizing power than Be2 plus. That's why calcium carbonate requires a higher temperature to decompose because less polarization means the CO bonds remain stronger. And hence they need a higher temperature in order to decompose. So this is how decomposition of carbonates, sulfates as well, nitrates as well will work. You will learn this at A level, all right? How this polarization works by the metal ion, but this is just an introduction to how decomposition will work. Okay, don't need to copy this down, don't need to memorize this. I'm just telling you why. Why is it that as you go down the group, generally the temperature will increase for decomposition of the carbonate? Okay, now with that, let's quickly move on to term 1, week 7, which is another interesting question, which we should spend some time annotating. All right. Okay, so let's move on. Now we are at term 1, week 7. All right, it's from Dunman Sec 2021. Now, again, you must pay attention to the header, but you don't see a clear header in this particular question. That's quite rare. Typically, we will put a header in. All right. Now, the header here that should have been the case is actually what we call the electrode potential. Okay, so let's put in the header. The header is actually electrode potential of different elements. All right. So again, electrode potential, never heard before. Never heard before, right? But immediately you know, okay, this is gonna be some redox thing. right? Even without the question saying you should know it's redox, because it involves electrochemistry, loss and gain of electrons, all right? Now, so this is about electropotential. So let's read, where is electropotential? Is there some definition or some trend that we can grab? So if you read, to find the trend, we look for words like more, higher, less, lower, such words, comparative adjectives. More. So this is my trend. Okay, the more negative the electrode potential, the more likely the metallic element will form ions and undergo oxidation. So let's look now. You look at the metals, right? They all have a different electrode potential. Look for the negative ones. Negative ones are like sodium, magnesium, calcium, lithium, potassium. These metals, what comes to your mind when you talk about all these metals? These metals are generally very reactive metals. Sodium, potassium, lithium, calcium, reactive. So the general trend you can see, which you also write, is that the more reactive the metal is, the more negative the E0 value. Now, electrode potential is called E0. So it's pronounced E0. It's pronounced as E0. It's not written as pronounced only. All right. Now, this is a general trend. Why does Mr. So add that this is a general trend? General means it's true for the majority. For the majority of metals, the more reactive the metal is, the more negative the E0 value of the metal. However, there are exceptions. General trend means there are some exceptions, and you can quite clearly see the exceptions already. Lithium is one of them, right? Lithium, you can clearly see it's minus 3.04 volts. It's very negative. It's the most negative, in fact, in the whole list. But lithium should not be as reactive as potassium. Lithium is less reactive, but yet the E0 is more negative. All right. So it's good to point out the exceptions even at this early stage, because you can be sure that it will be tested somehow. All right. Now, this also works for non-metals. You can clearly see for non-metals, there's also electrode potential, right? So you can compare the non-metals, the halogens. These are group 7, right? Bromine, chlorine, fluorine. The more reactive the halogen, the more positive the E0. Now, this is logical, because you know that fluorine is the most reactive in group 7. It's the most reactive means the E0 value is the most positive. Why? Because we read, if it's negative, it undergoes oxidation. But fluorine is group 7. It doesn't lose electron. Group 7, 7 valence electron, it gains electrons. So we know that halogens, they all gain electrons. Meaning, gain electrons. Gain of electrons is not oxidized, it's reduced. So this fully makes sense. It is not a positive potential. It's not a negative potential, sorry. It's not negative, because negative means it wants to be oxidized. Right? That's what the question told us. So why is it more positive? Because positive means it doesn't want to be oxidized. It wants to be reduced. Okay, so let's try to make sense of this. So you can see this is the second trend. It's also here, right? The more positive the electron potential, it will undergo reduction. Okay. All right. So at this stage, iodine is missing. Obviously, I know immediately they will ask you to predict the electron potential for iodine. Right? So iodine, you must know the trend. The trend is the more reactive the halogen, the more positive the E0 value. So iodine, where is it in group 7? Is it more reactive or less reactive? Well, we know. We have learned group 7, periodic table. Group 7, reactivity decreases down the group, right? So fluorine on top, most reactive. Astatine, least reactive. So iodine is in between bromine and astatine. So iodine's E0 value should be also in between 0.25 and 1.07 volt. The actual value is 0.54 volts for iodine. All right, so you need to suggest a value that is in between that of astatine and bromine, because we know that iodine is less reactive than bromine, more reactive than astatine. Okay. Now at this stage, can you just check that all the annotations are there? And if you have any questions, please ask now regarding the E0 value before we move on. You can type in the chat if you have a question regarding this. Nope. Now you can see, so this question effectively combines redox, electrochem, and periodic table. All right. Now this E0 value is a concept that's taught at A level to students. But actually, even at O level, you can begin to appreciate it. The moment you know the significance of the value of E0, you can quite clearly predict what is more easily reduced. For example, fluorine. Fluorine is very easily reduced because it has a very positive E0 value. On the other hand, something like potassium. Potassium is easily oxidized because the E0 value is negative. All right. Ken? So positive means reduced, negative means oxidized. Okay. Okay, so moving on, if there are no questions, the next section should also have a subheader. It's about atomic radius. So again, definition is the distance measured from center of nucleus to the valence electron shell in the atom. Okay, so you can quite clearly see patterns, right? As you go down the group, atomic radius increases. As you go from left to right, atomic radius decreases. Okay, so always write the trend down because it will help you. Okay, so moving on. Now, two students talk about the data presented. I think that whether or not the metal elements undergo oxidation, metal oxidation is linked to the position of metal in the reactivity series. Again, do you realize this goes back to the trend that we talked about? We had a general trend about metals, right? The more reactive the metal, the more negative the E0 value. That's a general trend. But look at what the student is saying. The student's statement doesn't have the word general. The student is just making a statement. There's no general. That means he's saying this statement for all metals, you know. Can we conclude that student one's statement is true? The answer, of course, is no. So student one is not correct because the general trend is true, but the exception, like lithium, makes students one statement incorrect. All right, so that's student one. All right, so you can see I've also quoted data from the table, so you need to do that. All right, so that's student one statement. Now you move on to student two. Student two's statement is about oxidation of metals again, but it's to do with the size of atoms, which is of course atomic radius. Again, can you see a trend? Again, there's a general trend, right? The larger the atomic radius, the more negative the E0 value. However, there are again exceptions. The exception is lithium. It's lithium again, right? Lithium is the problem. Lithium has a very negative electrode potential. So even though the atomic radius is small, smaller than sodium and potassium, but yet the electrode potential is more negative than sodium and potassium. All right. So once you recognize the exception, right, actually these 3-4 marks, if there were 4 marks, you could easily get. You know immediately the two statements must be untrue. Unless they added one important word. What is this important word that the students must add to make their statement true? Can you all type in the chat? What is this one word that both students need to add to their statements to make their statements true? Okay, some of you typed it already, only 1%. The rest, what is that one word that students must add? Okay, generally, okay, most of you type generally, yeah, okay. So the word is generally, all right? Can? Now, I'll just give you some time to copy this down first if you need to, okay? The good news is the rest of the questions are not super hard. I think most of you can easily work it out. Like B part 1, part 2, I think is quite straightforward. Okay, if I may move on, can you give me a thumbs up so that I know I can just move on for this? Okay, so student 1 statement is about position in the reactivity series, meaning whether the metal is reactive or not reactive. So if you notice lithium is actually below sodium in the reactivity series. But yet, lithium has a more negative electrode potential. By right, if it's lower, less reactive, it should have a less negative electrode potential. By right. But lithium has a more negative electrode potential. Therefore, you can see that the reactivity does not always correspond to how negative its electrode potential is. Okay? Now, and that's why most of our electronic devices today, like laptops, handphones, they make use of lithium-ion batteries. The reason why we use lithium-ion batteries is because lithium has a very large magnitude of electrode potential. You can see as minus 3.04 volts. This means that it has quite a large magnitude of the electrode potential, which gives rise to a larger potential difference or electromotive force for your battery. And that's how the modern lithium-ion batteries can power many functions of your laptops and handphones. You can watch YouTube, stream videos because of the lithium-ion battery. It gives rise to a large enough EMF, all right? And the EMF is because the electrode potential is this large in magnitude, okay? Now, we are going to quickly go through B. Now, B is quite obvious. It's just reading the data as the atomic radius increases for the halogens. As you go down the group, fluorine to chlorine to bromine, the atomic radius increases. The electrode potential becomes correspondingly less positive. And in fact, this one has no exceptions. So for the non-metal halogens, they actually follow this trend. There's no exception to this trend. Okay? And just now we said, right, for iodine, what is the electrode potential? Remember iodine? Iodine is in between bromine and astatine. So it must be in between the two values, in between 0.25 and 1.07. Specifically, you need to say or give me any value less positive than 1.07 and more positive than 0.25. Okay? Now you notice Mr. So doesn't like to say larger or smaller. This is because you already know the electrode potential has sign. It's like delta H. They have sign, right? So by saying it's larger or smaller may not mean a lot. Do you mean the magnitude or do you mean the value? Okay, so it's better to say less positive than plus 1.07, more positive than plus 0.25. Okay, be specific. Okay, that's B. Now, part C, right, actually has very little to do with the database question. Part C is really about what you have learned about preventing rust alloys, right? So you have learned the properties of high carbon steel, lower carbon steel, which is mild steel. Low carbon steel is called mild steel. All right. So part C, I'm not going to go through. It's from metals. So please try it yourself, and you have tried it. Later, go to the content library to look through part C yourself. Okay. And that brings us to the end of the review for term 1, week 7. Okay, before we move on to term 1, week 9, are there any specific questions about term 1, week 7's data-based question? Nope. Okay. If not, we're going to move on to term 1, week 9. Okay, I think we're doing good on time. Okay, I intend to leave more time for term 1, week 10, which has a longer data to read. Now, term 1, week 9 is not particularly difficult. It's all about reading the info that is present inside the text. So database questions, broadly speaking, there are 2 types. The first type is the type that's more mathematical, numerical. So like what you just saw with the E0 value, what you just saw with atomic radius or like ionization energy. These are more mathematical, right? There's some mathematical trend. The higher the reactivity, the more negative the electron potential, for example. There's some mathematical trend. That's the first type of database. The second type of database involves more reading of the text. So the text given to you here, obviously, is about blast furnace and iron. Because the first sentence already says that. So this one, immediately you must cross-reference. It's a bit like social studies. When you're asked to evaluate the reliability of a source, you cross-reference with other sources. You also have to cross-reference with your own knowledge, right? So similarly here, you cross-reference with your knowledge. Start thinking, what have you learned under blast furnace and iron? Try to recall everything you have, all right? Now, so that's for iron. Iron is produced in a blast furnace. You have learned that. You have learned all the reactions, all 5 reactions, in fact. Okay. But now let's throw a different thing in. Titanium. So besides iron, they want to discuss the extraction of titanium. So there are a few important things you need to take note of. First, highlight chemical names. Titanium is produced from the ore rutile. Rutile contains titanium dioxide, TiO2, dioxide, right? Immediately you see, oh my God, the melting point is so high. Clearly, the high melting point of TiO2 tells you it must have a giant ionic lattice structure. Okay? And that gels with what you have learned. You have learned that metals and non-metals, titanium, oxygen, they will combine together, react together, and the compound form will have a giant ionic lattice structure with strong electrostatic forces of attraction between the oppositely charged ions. Hence, a lot of energy is required to overcome the strong electrostatic forces of attraction between the ions, and so the melting point is very high. Okay? Now, so that's the first information. The second information, TiO2 cannot be reduced by coke. This is an important information. You know this because you know that coke is carbon. Coke is used to reduce a lot of things, including hematite, right? Coke forms CO. CO then reduces hematite. But titanium cannot be extracted the same way. Titanium cannot be extracted by carbon, which immediately means titanium is above carbon in the reactivity series. If it's above carbon, it cannot be reduced by carbon. So like aluminium, magnesium, calcium, they all cannot be reduced by carbon. That's why they have to be extracted by electrolysis, typically. So titanium is similar. It cannot be reduced by coke, means it's above carbon in the reactivity series. So now let's look. How is titanium really extracted? First, rutile is reacted with chlorine, and this produces titanium 4 chloride. You can write the formula if you want, TiCl4. You know that because it's titanium 4, means Ti4+. Right? Now, The titanium 4 chloride is then cooled and collected. Then the titanium 4 chloride is reacted with magnesium. Titanium 4 chloride and magnesium. This is important info. By writing the chemical formula out, immediately you realize, okay, this reaction clearly is something we have learned and seen before. You may not have seen titanium, but you have learned this before. Titanium is a metal. Magnesium is another metal. So why? Why do we add a metal to a compound of another metal? We have two metals, one metal, one inside a compound. This reaction has a name, and the name of this reaction is displacement. It works because magnesium displaces titanium from titanium 4 chloride. This means that magnesium is more reactive than titanium. All right. And so the products are predictable, right? TiCl4 plus Mg, titanium 4 chloride plus magnesium forms magnesium chloride. Magnesium chloride is not MgCl4. Magnesium chloride is MgCl2. You know that because it's Mg2 plus, Cl minus. Don't just because you saw Cl4, then you copy Cl4. It's not like that. You must think of charge. Magnesium is 2 plus, Cl is Cl minus, so MgCl2 plus titanium. Once you have this, then you start balancing. It's not difficult to balance. So the moment you have written this equation out, do you realize by highlighting chemical names and writing the equation, immediately the chemistry of this step is clear. It's basically displacement. Next, this occurs at a certain temperature in a sealed reactor for 3 days. It contains atmosphere of argon. Argon is inert. It's a noble gas. Why would you need inert noble gas atmosphere? There's only one reason. Whenever you use inert atmosphere is to prevent a reactive metal like sodium, potassium, calcium, magnesium from reacting. All right. And that is one of the questions asked later on. Okay. Finally, the reactor is allowed to cool and the titanium is separated from the other product, magnesium chloride, which we already know. Titanium, magnesium chloride. Right? So, A, explain why the production of titanium requires an atmosphere of argon. This is what we just said. All right? It prevents magnesium from reacting with other things in air like oxygen. Titanium as well. Titanium is quite reactive. Now, it's 2 marks. Clearly, you can't just say it prevents magnesium from reacting with oxygen. That's 1 point. Explain why argon. Argon is a noble gas, group 0. So it has a fully filled outermost electron shell. All right, so you need 2 points. 1 point for explaining why argon is inert, because it has a fully filled outermost electron shell. 2nd point from saying this prevents the magnesium and titanium from reacting with oxygen in air. All right, now part B. It's about melting points, right? They say that melting point of iron trioxide is higher than the temperature in the blast furnace, but yet it's in the molten state. That means it's already melted. Why? How come the melting point has changed, has become lower? What will lower melting point? So you think back to Sec 3, you have learned impurities in a mixture. Impurities in a mixture will lower the melting point of a substance. So in this case, you have impurities, right? You have impurities like hematite. Hematite has SiO2. Silicon dioxide is one of the main impurities in hematite. Okay? Now, moving on, I don't think the rest is very difficult. Part C is quite straightforward. Okay? Lime, you add lime or limestone, typically is to react away the acidic impurities in SiO2. This is what you have learned under blast furnace. Now, it's part D that's perhaps a little bit harder. All right. Now, part D, okay, why does titanium cost so much more than iron? So you got to relate costs to the chemistry of the procedure. So first, you know, to produce titanium, there are more stages, right? You can read It's like 3 stages easily. So when you have more stages, every stage has its own yield. If you have more stages, the yield is less and less. Okay? Therefore, it's less efficient. Okay, you can even quote the data. Okay, for example, iron, you can produce 480,000 tons of iron per day, because per day got 24 hours. Huh? Whereas titanium, not so good up, 1 ton per day only. Big difference. Next, blast furnace uses coke. Coke is carbon. Carbon is like very easy to find, abundant, and relatively cheaper. However, you cannot use coke for titanium extraction. Titanium dioxide cannot be reduced by coke. You need to use magnesium, a very reactive metal. So magnesium is expensive because it needs to be extracted by electrolysis. So you need an expensive magnesium metal to extract titanium. That's what makes titanium very expensive. All right. Okay. Now, this one is important. You should know by now, if you need a very reactive metal to extract another metal, the reactive metal is very expensive because it's extracted by electrolysis. So whenever you need sodium or magnesium or calcium to extract another metal, that makes the metal very expensive. Because sodium, magnesium, calcium itself are expensive. Just to buy 10 grams of magnesium will cost a lot of money. Okay. Now, part E, I think is quite straightforward. Let's go straight to part F also. Now, suggest the position of titanium in the reactivity series of metals. Please don't just say that titanium is above carbon. You need to be specific. You know it's above carbon because it cannot be reduced by coke. However, you also need to know that it's below magnesium because magnesium is able to displace titanium from TiCl4. So you need to have both in order to get the full credit. That's why it's 3 marks. Okay? So for part F, I think the tendency is for us to lose a few marks because you only say it's below carbon. Because you only saw that, oh, it cannot be reduced by carbon. But in reality, you need to pay attention to the fact that it's below magnesium as well. All right. Now with that, we have finished Term 1 Week 9's database. Now we'll move on to the final one, which is Term 1 Week 10 database question. Any questions at this point? Do you want to raise? If I may move on, can you please give me a thumbs up so that I know that I can just go on to the last one? Yeah. Now I'm just going to move on to the Term 1 Week 10. Now, Term 1 Week 10 is probably the most challenging. It's challenging and very daunting to most students because it requires about 3 pages of reading. All right. So again, let's revise from the start. What do you pay attention to? You will pay attention to the header, which quite obviously is bolded. It's about water treatment in this case, right? So it's about water. How do you treat, purify water so that it's suitable for drinking? The next thing you pay attention to is definitions, titles. Not titles, sorry, trends. So this one, does it have any trend? Not that I can see. I don't see words like more, higher, lower, less, right? But definitely there are definitions. Definitions like what? You see a lot of terms here, coagulation, what, BAC. What does it actually mean, right? You have never learned this before. No one would have learned this before. It's not in the syllabus. That means the definition must be given to you somewhere. Do you see that on the next page? Table 8.2 is the definition. You need this. If you don't read table 8.2, you wouldn't know what each of those terms mean. All right. So the definitions are in table 8.2, and that's where you need to find the answers later on for sure. So table 8.2 is important. So as opposed to looking at figure 8.1, it's more helpful to look at table 8.2 because that's where the definitions are in this case. So whenever you have a lot of info given to you, you don't just despair and give up. You need to know where to look for info. If you remember that you have to look for definitions and trends, you will know that table 8.2 is your best friend. You must look at it when answering the question. That's what you zoom in on. All right. Of course, next is the chemical names and numbers. And finally, last one is equations, right? So we shall see this later on. There are some numbers later on, like RF value, which of course relates to chromatography. All right, so this is just a diagram. Take a look at it, reservoir, then what happened before it goes to the home. More importantly, table 8.2 is crucial. You need to know numbers. 1 mm, greater than 1 mm, right? So you read, you need to know chemical names. Coagulants like aluminum sulfate is used to bind smaller suspended particles like sand to form larger, heavier clumps. Large particles settle to the bottom. Then after that, you got filters again, and it will filter out the finer particles up to 0.02 micrometers. Numbers. Is disinfected with chlorine or ozone. Finally, BAC. Finally, you know what BAC means. Biologically activated carbon. And this helps to remove natural organic matter. Then it's those with lime, chlorine, ammonia. Some of it you know, right? Chlorine is Cl2, ammonia is NH3. Lime is calcium oxide, by the way. Okay, so just by highlighting this, right, actually you have gotten the answer for part A and probably part B. Okay. Now you move on. Chemistry behind the water treatment process. So again, you read. Oh, so many things are. But when there's so many things, what do you focus on? You go back. You want to focus on the header. It's about chemistry behind the water treatment. You want the definitions and trends. Definition is like what? What is BAC? BAC is, that's what's in blue. BAC is used to separate dissolved organic compounds. Okay, the carbon is coated with bacteria. It breaks down the organic compounds. Do you see that this is how you basically do a summary in English as well? It's the same concept. You look for the main points. Okay? Okay? And in fact, what I've highlighted in blue is the answer to part B. Okay? Now, finally, you also need to take note of other chemicals like calcium oxide is added to adjust the pH. Why? pH is about whether it's acidic or basic. So now you got to think calcium oxide is basic. Basic means it's a metal oxide. Basic means it increases the pH. Right? Another way of putting it, neutralize the excess acids. And this is the answer to another one of those questions later. Okay, next, chlorine. Chlorine is added to destroy bacteria, and different fluoride-containing compounds such as this complicated compound and hydrofluoric acid are added to enrich the fluoride content, which helps to prevent tooth decay. Same as a toothpaste. Toothpaste contains fluoride. Okay, so can you see just by highlighting the chemical names, highlighting the definitions, you really zoom in. Do you realize the first paragraph is actually not very important? And even the second paragraph, you only zoomed in on a few important things. All right. Now moving on, you have the RF values. Okay, so again, you can see water in Singapore is safe to drink straight from the tap without further filtration. Not important. Not important for your chemistry question. What you need now is RF value. Oh my God. If you just look at the numbers, it's RF. RF means chromatography is coming in. So that's it. That's all you need to get from this whole section. Chromatography and RF. So a lot of you ask me, how do you finish the paper on time? How do you read fast enough? you need to zoom in on the things that are the most important. You see the table is about RF means the question is definitely about RF, chromatography. Okay. Now moving on. Part A. Water treatment involves sedimentation and filtration, but to facilitate this, you must first use aluminum sulfate as a coagulant. Use the data to suggest why coagulation helps to increase the effectiveness of sedimentation and filtration. So your answer obviously comes from where? The data they are suggesting is not numbers, you know. The data they are suggesting is what? Where do you see words like coagulation, sedimentation, filtration? If you look back at your paper, where do you find these words? It's here what? Table 8.2. Make sense? So this is where the answer for part A comes from. Need to read table 8.2. The data they are referring to is the information from table 8.2, not a graph, not a number. Okay? So this data is from table 8.2. Okay, so let's start now. How do we phrase our answers now? So first, coagulation. You have been told coagulation binds smaller suspended particles like silt and sand to form larger, heavier clumps. If you just look at this, I didn't even rephrase. It's the same as the table 8.2. Okay? Can? The larger clumps settle to the bottom of the tank and are removed. And this is called sedimentation. So again, can you see I just merely copied? I didn't do anything special. I merely copied what is seen under table 8.2 for coagulation and sedimentation. Now the next part is the one that's filtration. We must talk about filtration, right? These larger particles, how come filtration will become easier if they are larger? Because these larger particles have a size larger than 0.02 micrometers. Where on earth do I get this number from? I got this number also from table 8.2 under filtration. You are told, right? The filter membrane removes particles smaller than 0.02 micrometers. So because these are larger clumps, they are going to be larger than 0.02 micrometers. Hence, they can be more effectively filtered out by the membrane as they are larger than the pore size of the membrane. Okay, so how do you get the 2 marks? Actually, 1 mark it's just by saying larger, heavier clumps settle to the bottom. This is 1 mark. Next, by saying they are larger than 0.02, they are more effectively filtered out. Okay, so it's not very difficult to get 2 marks. Okay, it's like comprehension. Just need to copy from the right segments. Okay, next part B, use the data to explain the differences in how filtration and BAC helps in the treatment of water. Filtration, you know, right? Filtration, you should already know. Okay, using a membrane or using a filter paper, okay, you filter away insoluble solids. BAC is a new concept, but BAC is explained, right? Where is it explained? BAC is explained on page 29. So that's the one that we highlighted just now. BAC does what. So if you read page 29, find BAC, find that paragraph, highlight the keywords, then you will realize the difference. The first difference is filtration separates insoluble, or you can say larger insoluble solids from a mixture, while the BAC separates dissolved. Dissolved means soluble, organic compounds. So that's the first important difference already. The second important difference that you see, just go down the line, right? BAC is biologically activated versus coated with bacteria. Filtration, however, uses a filter paper, or in this case, you can use membrane to filter the mixture. While BAC uses carbon coated with bacteria in the separation. So what you use for the chemicals that you use are different. That's the second difference. Third difference, filtration. Filtration, when you separate sand and water, you get sand solid, water liquid. You don't change the chemical properties of the sand or the water. So we always say filtration, distillation, chromatography, evaporation, crystallization, separating funnel. These are all physical methods of separation that do not result in a chemical change. Filtration is not a chemical change. However, BAC, if you read, the bacterial coating helps to digest and break down organic compounds. BAC digests and breaks down organic compounds, which of course, when you break something down, you decompose something, that's a chemical change. So can you see that these 3 points can simply be obtained from that one paragraph on page 29? And that's why locating that one paragraph is crucial. Once you have located the right paragraph, finding the answer is straightforward. However, if you did not locate the right paragraph, you are going around in circles and never going to finish. So please make sure you annotate, like what I said, look for definitions. What is BAC? Then you zoom in on the paragraph already. Then immediately getting the answer will be much easier. Okay, so I shall give you about 1 minute. Take this down to check your answer. Okay, are we okay at this point to move on? Please let me know. If you have questions, you can also type in the chat. I'll attend to it. Okay, I'll take it. I can move on. Okay, Hemant, we will deal with that later. Okay. Again. All right. Now, part C. Explain how and why calcium oxide helps in the adjusting of the pH of water. The how and the why is important. Many students don't understand why is there 2 words in the first place. Why don't you say explain how or explain why? Is there a difference? There is a difference. Calcium oxide, the how is the mechanism. The mechanism is it neutralizes the acid. That's a how. But why does it neutralize the acid? This is because it is a basic oxide. This is the why. Hence, it helps to neutralize the excess acids in the water and increase the pH. So this is the how. You must have both. Okay? If you don't have both, you won't get the 1 mark. And that's why it's important to realize what are you talking about. The why versus the how is not the same. Okay? Now, part D, I shall not go through. Please just find out the percentage by mass of fluorine yourself. The formulas are given, so it should be quite straightforward. All right. Part E, I'm not going to go through as well. Part E is RF value. All right. So you need to use a ruler to really go and measure, all right, the height of the solvent front as well as the distance that's supposed to be traveled by the ion. Okay. Ken? So please make sure you do part E properly using a ruler. So part D, part E, I will not go through. Now let's go straight to part F once we are done with part C. And that nicely brings us to the very last part. Now, part F may look very, very intimidating as well, but actually it's not so intimidating. So first, you read, a company selling a special type of household water filter claimed that a sample of Singapore's tap water was tested and found to contain a high concentration of ions, and these are the ions, right? Calcium, lead-2, aluminium, and so on. All right. The company made another claim that its water filtration system uses alkaline filters, all right, containing hydroxide ions to remove all the positive metal ions, all positive metal ions. Right? Okay, so actually one of you had asked me this question earlier. I realized that I may not have answered it fully. Now, there are two claims made here. First, the claim that it has a high concentration of these ions. The second claim is that the alkaline filters can remove all the metal ions that are positive by forming precipitates that can be filtered away. So we're going to tackle each claim individually because there's an error in each of the company's claim. So let's do the first claim. The first claim that there is a high concentration of calcium and lead-2 ions is incorrect. Because, now why is it incorrect? Why do I single out calcium and lead-2? We got to think, concentration means it's dissolved in water, you know. Look at calcium. Does it form an insoluble salt with any of the solids? Calcium and sulfate together forms an insoluble salt. Lead and sulfate as well. Lead and chloride as well. And so what if they are insoluble? So we have learned, right? If something is insoluble, it should not be aqueous, it should be solid. If they are solids, they will precipitate out and be removed before going to households. Remember, this is household tap water. That means it has already been purified through all those steps, you know. If it's insoluble, it would have been filtered away long ago in step 4, right? Filtration. It wouldn't even have reached the household tap water. Household tap water means at the end, at the end of step 10, how can these ions still be present in step 10? In step 4, these ions will have precipitated out together with the sulfate and chloride. All right. And if they are precipitated out, they are filtered away already, removed by filtration. So the first claim is not correct. To add on, the second claim, the second claim that all the positive metal ions form precipitates, PPT, that can be filtered away is incorrect. Okay, why is it incorrect? Because, for example, not Ca, sorry. What's remaining is Al3 plus, right? Al3 plus is able to form a white PPT that is soluble in excess NaOH. So it cannot be filtered away. Now, I'm making an assumption that these hydroxide filters refer to NaOH. I'm making an assumption. All right. You can make an assumption that it's ammonia as well. If it's ammonia, this claim is still wrong. Ca2 plus also does not form PPT if aqueous ammonia is used as a source of hydroxide ions. Okay. Now, the idea is, this is entirely, you realize, this chapter is QA. This question is all about QA. Whether you know something is soluble, insoluble, whether you know something forms a PPT that's soluble in excess NaOH, whether it doesn't form a PPT in the first place. All right. Now, you have to make certain assumptions, I agree, because you are not certain if they are referring to NaOH or ammonia, but you realize even if you had assumed it's ammonia, the statement is still incorrect because Ca2 plus doesn't even form a PPT if you assume it's ammonia. If you assume it's NaOH, the statement is still wrong because Al3 plus will form a PPT that is soluble in excess NaOH. So it can't be filtered away either. So the statement will always be wrong regardless of whether it's NaOH or ammonia. All right, Ken? Now this 3-mark question, I would say, is quite challenging. It's not easy. You must start thinking about QA in the midst of every single thing going on in this question. But you know it's about QA because you can see hydroxide. You can see whether it's soluble or does it form an insoluble precipitate. So all these keywords tell you that, okay, it's a test for the metal ions, which I've learned under QA. All right. Okay. Now, if I may move on to one very short last thing, can you give me a thumbs up when you're finished copying this, that is. Okay, so I'm going to move on. What do I move on to? Now I'm going to move back to the very first cover page. Now the whole idea of letting you all do database questions by term and writing out the cover page is so that you can easily access and revise the appropriate question that you need before the O-levels. Now, every single database will test a different combination of topics, which is already listed there. All right. So that one should be quite straightforward. If you wanted to find a database on bonding, maybe you can go back to week 2, right? Find a database on electrochem, maybe week 7, and so on. But what I want to point your attention to, which you don't have to copy down, this is in your content library. These are the skills from your syllabus, all right? So as I've mentioned in class, pure chemistry is not entirely about memory work. It's not entirely about content. In fact, they want to assess your skills in handling information and solving problems. All right. There are 7 different skills here if you like. 1, 2, 3, 4, 5, 6, 7. All right. You can read it yourself. All right. And these skills together will take up 55% of your marks. So as you can see, right, if you just know the content but don't have these skills, you won't score very well. And that's why we are practicing database to sharpen some of these skills. If you read some of these skills, locate, select, organize info. This is why we annotate, right? The annotations we did just now. You pay attention to the title, pay attention to definition and trends, pay attention to chemical names and numbers, pay attention to the chemical equations. This is how we locate information. If you think through, just now the term 1 week 10 got such a long passage to read. You merely focus on just 1 paragraph on BAC because you know that that is where you locate the information and select the information. Okay, next skill, translate information from one form to another. Maybe you have to translate it from a graph into words. Maybe you have to translate from words into an equation, mathematical equation. All right, manipulate data. We have done a lot of that, right? Find gradient or like come up with a trend. Identify patterns and report trends and draw inferences. We did so much of that today. Writing out the general trend. That's a good way to test skill number 4. Provide reason explanations. Skill number 5. That is what we also did today, right? Explain why this statement is true. Explain why this statement is not true. Provide explanations for relationships and patterns. Reasoned explanations, meaning you need to use data. All right. Okay. Finally, make predictions, solve problems. So these are the skills that are tested. Okay. Now, if you look back at your database questions for term 1, they are not randomly selected. Okay, I did not select them randomly. They correspond to these 7 skills. Okay, you don't have to copy down. It's inside your content library. I'm just going to quickly tell you what the skills are. All right. Term 1, week 1 is skill number 1. Okay, locating and selecting info. This is in the form of a flow chart. Okay, so term 1, week 1 is a flow chart. You need to revise this. How do you read the flow chart and extract information? Term 1, week 2 is skill number 4 and 5. All right, which is to provide reason explanations and identify patterns. Term 1, week 3 is skill number 5, providing reason explanations. Term 1, week 4, 4, 5, and number 7. Okay, solving problems as well. Term 1, week 5, skill number 5 and 6. Providing reason explanations for relationships and patterns, and also suggesting hypothesis. Term 1, week 6, selecting info and solving problems. Term 1, week 7, we go back to reason explanations and hypothesis. Term 1, week 9 is the one that extraction of iron and titanium just now is selecting information, reading a whole wall of text, selecting information. Finally, term 1, week 10, selecting information, translating the information from the table onto a prose form, and finally, providing a reason explanation. So hopefully you can see a variety of skills which are being tested. Okay? So with this, right, I hope this gives you a head start as to what you can do for database from now on. Now, whenever you do database, you must remember these 7 skills. You have to remember that these 7 skills are not just in database. They are 55% of your total marks. That means beyond the database question, other questions will also be like this. Okay, and that's not surprising. You have already been exposed to database questions beyond just the 12 marks. You may have other marks, okay, in your section A of paper 2, which are also allocated for the data intensive questions. So these are the 7 skills that you need to know. Now, how do you recognize a database question? Generally speaking, the question will start with predict, deduce, suggest, calculate, or determine. Another word that you should add here is evaluate. These words, if you see them in a question, most likely it's a database kind of question. Okay, so that's all I wanted to go through for the term 1 database questions. Okay, I shall stop the recording now. Thank you.